Welcome to the next week in the course Basics of Mechanical Engineering 1. We are discussing the components and systems of the machines in this part of the week. For example, we will discuss couplings and shafts in this lecture. Further lectures in this week would include keys, belts, pulleys, and different other components or the systems which are there in the machine development. So, coupling and shafts, the contents in this lecture would flow like this. We will give you introduction to the couplings. What is the need of coupling? Couplings are generally used in machinery to connect shafts or to transmit power. It has several roles. For example, two shafts are there, which is a play between shafts. Coupling helps to cover that play. Then the coupling helps to have a flexibility between shafts. Couplings helps to curb the vibrations if those are there. Then they protect the components from the impact or torque overload, etc. The equipment performance is also increased when you use couplings also. So, certain design considerations are there when we design couplings. We will also compare couplings to the chain drives. Chain drives will be discussed in the coming lectures in this week. Then shafts and flexible shafts and its applications will be discussed. Design and material considerations for flexible shafts and introduction to shaft design would be covered. Material selection for the shaft would also be covered. Types of shaft and torsion in the shaft, we will see certain numerical problems here. Different kinds of couplings are there, flexible coupling, rigid coupling. In those further itself the classification could have single joint coupling, or we call them as one piece split clamp coupling or two piece split clamp coupling. It could be 3 piece, 4 piece, multiple couplings could be there. Let us have a brief introduction on what coupling is. Couplings, as mentioned here, are mechanical devices used to connect two rotating shafts to transmit power. It could be used to transmit power, to transmit torque, and transmit motion from one shaft to another. They are essential in systems where shafts are misaligned or where we need for vibration, damping, or flexibility. There are multiple types of couplings. These are the few couplings which are shown here. You can see this is a very rigid coupling here. There could be some flexibility with a washer put over here, or maybe we could put a membrane which is little flexible. So, there are different kinds of sub couplings are there. Types of couplings could be rigid coupling, flexible coupling, and fluid couplings, where it completely automatic transmission is expected. That is fluid coupling. First is rigid couplings. Rigid coupling is used to connect perfectly aligned shafts. When the shafts are perfectly aligned, that is, there is no misalignment, then we use rigid couplings. When the axis of the two shafts are perfectly aligned to each other and those are exactly horizontal, then only rigid coupling could be used, because there is no play that is allowed here. They do not accommodate misalignment and are used in applications where precise alignment is crucial. Here certain examples where these are used are sleeve couplings, or it could be clamp coupling, which an example given here. Then comes flexible couplings. These couplings allow for a small degree of misalignment between connected shafts. They are commonly used in machinery to absorb shock and vibration. So, here because flexibility is now allowed to some degree, so there could be certain couplings such as we have universal joint. Then we have gear coupling, because vibrations in gears are there, so those could be covered using this kind of a coupling. Also we have elastomeric couplings. When I say elastomers, they are materials or polymers such as rubber, So, rubber like material which has property that can be stretched. When stretched, even then it comes back to its original position. So, flexible coupling is there that accommodates the misalignment between angle, between axis or so. Similarly, we have fluid couplings. Fluid couplings are couplings that use hydraulic fluid to transmit torque between shafts, allowing for smooth and controlled acceleration. So, smooth acceleration, like nowadays we use hydraulic brakes in vehicles, so in automobiles or so, where the smooth stopping of the car should be there, or deacceleration which is there in the car should be very smooth. So, hydraulic systems are there in the bikes itself. The bicycles use now hydraulic brakes, where these kinds of couplings are there. The fluids helps to have a smooth and controlled acceleration or deacceleration. So, they are often used in automotive and industrial applications where torque transmission with slip is needed. For example, in automatic transmissions. In automatic transmissions, because these are controlled by an automatic system, manual system is not there. So, it is expected to be smooth, so that a certain jerk does not happen. Then let us now see the certain applications of the couplings. Applications could be in pumps, in compressors, in gearboxes or so. For example, in pumps, flexible and magnetic couplings are commonly used, and these help to connect motors to pumps. This allows for misalignment and reduce the vibration. In compressors, couplings transmit power from the motor to compressor. From the motor to compressor unit, the power is transmitted, which enables efficient torque transfer even when shafts are slightly misaligned. You can see from motor, this is the motor and this is our compressor unit. So, power is transmitted here. Then in gearboxes, gearboxes often use rigid couplings to transmit high torque from motors to the gearbox. So, this maintains precise alignment. Maintaining precise alignment. Next comes design considerations in couplings. First and the foremost thing is alignment. Proper alignment between connected shafts is critical for efficient power transmission. Rigid couplings require precise alignment. So, while flexible couplings can accommodate some or slight misalignment. Flexible couplings may accommodate some or slight misalignment. Similarly, load capacity. Selected coupling must be designed to handle the transmitted torque or transmitted load without failure. Rigid couplings are suitable for high torque applications because those are very rigid. In flexible and fluid couplings, loads are varying. Varying loads, because flexibility is there, it is not completely rigid transmission. Varying loads are there in flexible and fluid couplings. Then comes flexibility. Some applications require couplings that can flex to accommodate angular or axial misalignment, vibrations or thermal expansion. Flexible couplings are ideal for this use. The word flexibility means here flexible couplings are only used. Then comes vibration and shock absorption. In systems where vibration and shock are common, elastomeric or fluid couplings are used to absorb and dampen these forces, prolonging the life of the machinery. Then brief comparison between chain drives and direct couplings. Efficiency. Chain drives are more efficient as they do not slip, unlike belt drives. Direct coupling is even more efficient but rigid, with no flexibility for distance or alignment issue. So that means if I talk about slip, maximum possible slip that is there is in belt drives. This is more than what is there in chain drives. This is even more than some of the rigid couplings. This is about the slip. Then comes durability. Chain drives last longer but require more maintenance. We'll talk about chain drives because the weight to the design ratio, the overall weight of the system increases when the chain drive is used. Belts are lighter in weight, so belts are also quieter. Chains are a little noisy. Belts are quieter, but those wear out faster and need regular replacement. Belt drives are the most economical because we do not have to design any serrations or any accommodation of the coupling or the chain components there. So belts are most economical, followed by chain drives, and direct coupling is expensive but efficient in specific applications. So if I say cost, again I will put it as belt, chain, then coupling. So this cost is lesser, belt is lesser than chain is lesser than the couplings. This is cost, this is slip, that is being allowed here. Now comes the general shafts introduction. A shaft is a rotating machine element, usually circular in cross section, which is used to transmit power from one part to another, or from a machine which produces power to machine which absorbs power. A machine that produces power, I would say your engine in your automobile, that produces power. From there the transmission torque is there, that transmits the power to the wheels. So that absorbs the power and try to rotate the wheel, wheels are rotated and the automobile moves. So role of shafts in power transmission. Shafts are critical mechanical components used to transmit rotational motion and power in machinery. They connect various machine elements such as gears, pulleys, couplings, ensuring efficient power transfer from one component to another. Their major functions that it does is transmit torque and rotational motion between connected parts, allowing for functioning of engines, machines and vehicles. Common uses of shafts are given here. These are found majorly in vehicles, for example drive shafts, then industrial machinery, conveyor systems and pumps. They must endure various stresses like torsion, bending, axial forces during operation. So these all become the design consideration when we try to design a shaft. Let us try to see the types of shafts. Shafts could be of multiple types. It could be solid, it could be hollow, fixed or rotating. So what are solid shafts? Solid shafts are widely used in machinery where high strength and rigidity are required. Like we talked about the rigid coupling, solid shafts are used where high strength is required. They are simpler to manufacture and offer high torsional stiffness, making them suitable for transmitting large amounts of torque. Because these shafts have no joints, these do not have any angles between them in general. So these are straight rods which are developed for the rotational motion. So they are solid and they can transmit power with high strength and rigidity. Then comes hollow shafts. We call them hollow shafts or hollow pipes are there. This could be used as shafts as well. Hollow shafts have an empty core and lighter than solid shaft. The lightweight or strength to weight advantage or strength to weight ratio is always better here, and these are often used in applications where weight reduction is the requirement or weight reduction is critical, that is mentioned here, such as in aerospace, in automotive systems or so, where weight is to be reduced but strength is required equivalent. So there the hollow shafts are used. Despite their lower weight, they maintain good torsional strength. This is again law of physics. You understand, when for the same material, when the pipe is hollow or a shaft is hollow, it would have strength even higher than what is there in the solid shaft. Then comes fixed shafts. Fixed shafts are stationary and serve as support for rotating components like pulleys or gears. These shafts do not rotate but carry load of rotating elements. So, fixed shafts are there that only carry loads, they do not rotate. Rotating shafts are there which are actually rotated. Rotating shafts are responsible for transmitting rotational motion and torque. For example, this is a rotating shaft. From a motor, we have a shaft here and this is a coupling. The motion is being transmitted here. They are subjected to torsional stress and bending loads due to their rotation and often used in motors, gearboxes and drives. Let us try to now see the properties of the shaft material, that is the criteria for selecting materials for shafts. First thing is strength. The shaft material must be strong enough to withstand the applied torque and forces without failing. That is, high tensile and shear strength are critical for reliable performance. Fatigue resistance, like we took the example that we took the test for the strength of the components in like tensile test, compression test, those were for the shafts. Bending test was also for the shafts. What is the bending strength there? So, those were all for the components such as shafts. Similarly, fatigue strength is there where cyclic loading, that is continuous vibrational loading is there, that is tested on a components where shafts experience cyclic loading. So, fatigue resistance which can lead to fatigue failure, that is tested here. Materials with high fatigue strength such as alloy steels are preferred for applications with repetitive loading. So, this is fatigue resistance. Also certain other criteria such as toughness, wear resistance, cost etc. or machinability, those are there. Let us see those. Toughness is necessary to resist sudden shocks or impact loads, like the impact load that we had a experiment demonstrated in the previous weeks. A shaft material that absorbs energy without fracturing is ideal in dynamic systems. Without fracturing means for the specific load for which is designed. Then wear resistance, materials that are resistant to wear and surface degradation extend the lifespan of the shaft, because the surface of the shaft is prone to corrosion, is prone to rust or so. So, wear resistance and surface degradation should be the property that is required. Then comes cost and machinability. We could use shafts made of alloy steel or wire, but that shaft would be very expensive. Machinability of those shafts would be very tough to be taken off. So, then cost becomes a factor. While performance is important, cost and ease of manufacturing also influence the material selection. Here common materials include carbon steel, alloy steel, stainless steel or so. For example, carbon steel will be very expensive, that can be used at places where even stainless steel will be used, but this is cost inefficient if we do it. So, wear resistance, if I say, this is more critical when we talk about bearings which involves friction or other moving parts. Parts that involve friction. Similarly, we talk about cost and machinability. So, there should be a balance between cost, machinability and performance. Then comes flexible shafts. These are shafts which are flexible, you could see. Flexible shafts are mechanical components designed to transmit torque and rotational motion between 2 points even when the shafts are bent or misaligned. These are completely bent or flexible shafts here. This is a flexible shaft here. These shafts consist of wound steel wire or other flexible materials that allow for bending without losing the ability to transfer power. Allow for bending is the critical or the key word here. So, importance of the flexible shaft in torque transmission. Flexible shafts enable power transmission in systems where direct alignment of driving and driven shaft is not possible, offering flexibility. So this reduces the need of precise alignment. They accommodate angular, axial, and even offset misalignments, which make them versatile for applications in tight spaces or systems that require rotational motion in multiple directions. So these are flexible shafts. These are used in multiple places, such as in automotive systems, in remote power transmission, in hand tools for drilling or so. Flexible shafts are used in speedometers in automotive systems, in throttle linkages and transmission systems where direct drive connections are difficult or impractical. For example, this is, you can see, a accelerator. You call it a wire or you call it shaft in automobile systems, in speedometers that is here. Then remote power transmission. Flexible shafts are employed in applications where power needs to be transmitted over a distance, such as in conveyor systems or in automated manufacturing lines or so. Hand tools for drilling. In hand tools like flexible drills and grinders. Flexible shafts allow the user to reach tight or awkward spaces, that is intricate or difficult to reach spaces which are there. In those cases, flexible shafts provide greater maneuverability. Let us see design considerations in shaft. Like we talked about the strength, the load that shaft could withstand is a consideration. Shafts must withstand various types of load. For example, axial loads in the shaft's length direction and radial loads in perpendicular to the shaft axis. So in this direction it is axial, in this direction it is radial. Torque. Shaft transmit power through torque, which induces shear stresses. Fatigue. Cyclic stresses can lead to fatigue failure to the shaft. This must be designed with adequate safety. This is discussed when we talked about the shaft. So regarding the flexible shafts, when we try to talk about, the proper design ensures shaft can carry torque without failure. So deflection in the shaft, that what is the allowed deflection that is there. Excessive deflection should not be there. Whatever tolerance limits are there for deflection, those are only taken. There are tolerances or tolerance limits between which the flexibility is allowed or deflection is allowed. Stress concentration, sharp corners, keyways and other discontinuities may result in localized stress concentrations. So these should be avoided when we talk about the shaft design. If not avoided, the stress concentration areas should be minimized. Then regarding the flexible shafts, when we talk about the design consideration flexible shaft, geometry. The diameter of the flexible shaft directly imparts the torque capacity. Larger diameters can handle higher torques, while smaller diameters are more flexible but with lower torque limits. Then winding pattern of the wire, that is, it could be spiral or helical. This affects the shaft's flexibility and the smoothness of power transmission. That is, what is the geometry, whether it is wide, whether it is thin, that is smaller in diameter, whether it is spiral or whether it is helical. So these determine the strength of the shaft. Other than those, the regular criteria that we saw in the previous design for flexible shafts as well, the performance considerations such as the torque capacity, the bending radius, the fatigue resistance are taken. In the torque capacity, the material and size of the flexible shaft determine how much torque it can transmit. Overloading the shaft can lead to failure or reduced efficiency. Then comes bending radius. The minimum bending radius must be considered to avoid permanent deformation or stress fatigue in the shaft. Fatigue resistance, this is again repeated flexing can lead to fatigue and failure. Shafts, those are rotating and vibration is there. Fatigue failure is very prominent there. So that is why fatigue is coming time and again when we talk about the regular shaft design, when we talk about couplings, when we talk about the flexible shafts. So fatigue testing for the shafts becomes a critical characteristic to prefer a long lasting performance in the shaft. Materials used for shafts could be carbon steels, for example AISI 1040 or 1050. This is known for good strength, ductility and machinability. Alloy steels, for example AISA 4140 and 4340. These provide better strength, toughness and wear resistance than carbon steels. Then comes stainless steel. These provide excellent corrosion resistance, often used in environments where corrosion is a concern. So stainless steel is used where the resistance to corrosion is required more. Then comes aluminum alloys. These are used for lighter loads and applications requiring high strength to weight ratios. Aluminum, because it is lighter in weight than the steel components. So when the strength to weight ratio is a concern, aluminum alloys are used to design a shaft or to take it as a material for the shaft. Then comes nickel or titanium. Titanium, again it is used when strength to weight ratio is required, but machinability is an issue. I will put it here. Machinability, that is difficult. I will put an arrow downside when we talk about titanium alloys. These are employed in high performance applications, especially where strength and temperature resistance are critical, because high temperature strength or strength at red hot temperatures, that is also high for titanium alloys. Then when we talk about materials for flexible shafts, steel and stainless steel are generally used. These are most common materials for flexible shafts due to their high strength, durability and ability to resist wear and fatigue. Then comes composite materials. Composite materials are lightweight, so lightweight composites and polymers are used for applications requiring corrosion resistance and lower weight. Then comes flexible steel wire. The core of many flexible shafts consists of a tightly wound steel wire, which provides the ability to flex while maintaining the required torque transmission properties. Design considerations for flexible shafts. Let us talk about the applications of flexible shafts. Flexible shafts are used in devices such as optical systems and robotic arms, where precise control and motion in multiple planes are required. In medical devices, there is also used where in endoscopic instruments, when the shaft goes inside the body through the anus or maybe sometimes to the mouth, flexible shafts enable the transmission of the torque to tools inside the body, allowing surgeons or for the diagnostic to perform minimally invasive procedures with high precision. So without cutting the body parts, shafts allows to go inside and record the images. Now, these are certain applications or the major applications for the flexible shafts. Now let us try to talk about the torsion in shafts. So I will immediately focus this on the twisting movement only, shafts which are subjected to twisting movement. When the shaft is subjected to a twisting movement or torque only, then diameter of the shaft may be obtained by using torsion equation, which we know T by J is equal to tau by R, where T is twisting movement that is mentioned here or torque acting upon the shaft, J is polar moment of inertia of the shaft about the axis of rotation, tau is the torsional shear stress and R is the distance from the neutral axis to the outermost fiber. So if I see this diagram, this R is here, this is my R, which is D by 2, that is half of the diameter, this is D. So R is equal to D by 2, which is given here, where D is diameter of the shaft. Taking this, we know that for a solid shaft, the polar moment of inertia J is equal to pi by 32 into d power 4. So now equation 1 which is there, so this is equation 1, that could be rewritten here as tau by j, that is j is here pi by 32, which comes from here, and we put here r as d by 2. This is r. This gives me T, that is twisting moment or torque acting upon the shaft, is equal to pi by 16 into tau into d cube. From this equation, we may determine the diameter of the round solid shaft T. We also know that for hollow shaft, polar moment of inertia is this, because when we talk about the hollow shaft, in hollow shaft there are two diameters, that is d outside and d inside, or we call it DO or D1. DO is the outside diameter and D1 is the inside diameter. So it becomes the J. So J, that is polar moment of inertia, here becomes pi by 32, d outside power 4 minus d inside power 4. Here again R, that is radius, is equal to d outside by 2. Now I put the value for the hollow shaft here. Hollow shaft, where T by J is equal to tau by R. This is R for hollow shaft. This gives me this relation into this form, and also we put K as ratio between the inside diameter and the outside diameter, that is K is equal to D1 by DO. If I put D1 by DO, this ratio could be put here. So what I did, I divided this whole by DO. So I got DO here and DO here. So D1 by DO becomes my K. So here and here I put the value of K. I got this equation as pi by 16 tau TO cube into 1 minus K power 4, where K is the ratio between D1 and DO. So from the equations 3 and 4, this becomes equation 3, this becomes equation 4. The outside and inside diameter of a hollow shaft may be determined. It may be noted that the hollow shafts are usually used in marine work. These shafts are stronger per kg of material than the solid shafts, and they may be forged on a mandrel because those are hollow. So when the shafts are hollow, for example, this is a shaft, this is a mandrel, this could be mounted on a mandrel. So these shafts are rotated, and there is a mandrel that could be stationary, that could even rotate with the shaft. So thus making the material more homogeneous than would be possible for a solid shaft. So this is a major application of the hollow shaft, that could be forged on a mandrel. When a hollow shaft is to be made equal in strength to a solid shaft, the twisting moment of both the shafts must be same. In other words, for the same material of both the shafts, we are equating for the hollow shaft and for the solid shaft. So this is what I have for the hollow shaft, and this is what I have for the solid shaft. So to design them for equal strength. So for the material to be of equal strength, these are equated, which is pi by 16 tau dO power 4 minus d1 power 4 by dO is equal to pi by 16 tau into d cube, where this d is for the solid shaft and dO and d1 are for the hollow shafts. Next is twisting moment may be obtained by using the following relation. Here we know that the power transmitted in watts by the shaft is P, that is equal to 2 pi n into T by 60, or we can write it as T is equal to P into 60 by 2 pi n, where n is the speed of the shaft, that is rotations per minute, T is the twisting moment in Newton meter. In case of belt drives, the twisting moment could be written as T is equal to T1 minus T2 into R, where T1 and T2 are tension in the tight side and slack side of the belt respectively, and R is the radius of the pulley. Let us try to solve a few numerical statements to understand the twisting moment and the torque that we have just understood in the previous slides. That this is a problem statement that is given. A line shaft rotating at 200 rotations per minute is to transmit 20 kilowatts of the power. The shaft may be assumed to be made of mild steel with an allowable shear stress of 42 megapascal. Determine the diameter of the shaft, neglecting the bending moment of the shaft. That is, what is question mark is diameter of the shaft, and what is given is capital N, that is 200 RPM, and we have gotten the power is equal to 20 kilowatts. Also, it is given the allowable shear stress, that is tau is equal to 42 megapascal, which is equal to 42 Newton per millimeter square. So, torque transmitted by the shaft, which is given in the previous slide, that is here, this formula could be used. This is equal to P into 60 by 2 by N. So, I will write it as torque transmitted, this is equal to T, that is equal to P into 60 by 2 by N, where all the units are there in the required form. So, we will write it as P is equal to 20 kilowatts, it is 20 into 10 raised to power 3 watts. So, this is 20 to 10 raised to power 3 into 60 by 2 into pi into N is 200. This gives me the value of the torque as 955 Newton meter, or I could put it as 955 into 10 raised to power 3 Newton millimeters. Now, I need to calculate the diameter in millimeters, that is why I converted this into millimeters. To calculate the diameter, let me put it here, this value, that is the torque transmitted, torque transmitted, that is T, this is equal to pi by 16 into tau into d cube, which is the relation given here. Here it is given for the solid shaft 5 by 16 into tau into d cube. So, this we have put in our numerical problem. So, this gives me T, this is equal to 955, this into 10 raised to power 3, this is equal to pi by 16 into tau, value of tau is 42 megapascal into d cube. This gives me d cube is equal to 955 into 10 raised to power 3 into 16 by 42 into pi. This gives me the value of d as 48.7, or we can say it equivalent to or somewhat close to 50 millimeters. This is a solution. Let us see another problem statement where it is given a solid shaft is transmitting 1 megawatt at 240 RPM. Determine the diameter of the shaft if the maximum torque transmitted exceeds the mean torque by 20%. Interesting problem. Take the maximum allowable shear stress as 60 megapascal. So, it is given a percentage exceeding in the torque. So, here what we are given is, we have been given power P is equal to 1 megawatt, right, or I can put it as 1 into 10 raised to power 6 watt. Then what I have been given is the RPM, that is N is equal to 240 RPM. Then it says T maximum is equal to 20% of the exceeding, that is is 1.2 times, that is 20% exceeding the T mean, and we have been given the allowable shear stress, that is value of tau as 60 megapascal, which is equal to 60 newtons per millimeter square, and we need to find the diameter of the shaft. Diameter of the shaft is what is to be found. So, let us put the torque transmitted again. So, T mean is equal to power into 60 by 2 pi n, which is equal to 1 into 10 raised to the power 6 into 60 by 2 into pi into n is 240. This is equal to 39784 Newton meter, or is equal to 39784 into 10 raised to power 3 Newton millimeters. So, maximum torque transmitted that is given, that is T max is equal to 1.2 into T mean. This is equal to 1.2 into the given value 39784 into 10 raised to power 3, that is equal to 47741 into 10 raised to power 3 Newton millimeters. So, also we know maximum torque is there for the design. So, maximum torque is now here T is equal to pi by 16 into tau into d cube, which this is equal to pi by 16 into value of tau is 60 and d I have to find value of t is given, which is 47741 into 10 raised to power 3. Similar to the previous numerical, we will find the value of t. Here I have gotten t cube is equal to 47741 into 10 raised to power 3 into 16 by pi into 60. This gives me value of t as 159.4, or say this is equal to 160 millimeters. These were a few numericals. So, let us try to just recapitulate what we discussed in this lecture. The questions that you could ask yourself or try to intrigue yourself to solve while going through this lecture and also going through the reference material. First is, what is the purpose of coupling in a mechanical system, and when would a coupling, that is flexible coupling, preferred over a rigid coupling? What is the role of shafts in power transmission? What are the key factors to consider when designing a shaft for strength and stiffness? How do flexible shafts transmit torque through curved paths? And in which industrial application they are commonly used? Curved paths could be, as I talked about the industrial application, talked about the applications in automobile or so. You can answer those applications specifically where those are used. What factors influence the efficiency of power transmission in belt drives and how it can be improved? What is the importance of selecting right material for shaft design and what properties are crucial? When I say right material, we talked about both rigid and flexible. So, all the characteristics or the design considerations which were there, try to list them down. So, what are the uses and applications of solid and hollow shaft? The strength to weight ratio you can mention. Where do fixed and rotational shafts find their application? How do you calculate the torsional stress in solid shaft under a given torque? And these are a few reference books which are taken for this PPT presentation, and also certain other references were taken from the internet. All the references or the sources are given beyond the figures which are presented in the different slides here. With this, I am closing this lecture. I will meet in the next lecture where I will talk about the keys and other components in the shaft systems as well which are used. Thank you.